Okay, hello again. So I stopped the video and I'll resume now because I realized that certain things were going to go, I needed to be reordered. And so actually, these will be concepts for 4, 5, 6, 7, and 8. And I changed the order so that we need to talk about what is a unit vector. What is a unit vector? How do we normalize a vector? So remember up here we had the length of a vector, given by this formula, the dot product of a vector with itself, and then square root, the sum of the squares of the components, that's the definition of dot product with itself, and then the square root. Now, what if we want a vector to have length 1? So, for example, like the vector 4, 1, let's say that's the vector. Then the length of this vector is the square root of 16 plus 1. So that's square root of 17. Okay? That's not 1, right? Square root of 16 is 4. So this is something like 4.1, 4.2, something. It's not 1. So, if we drew this vector, it'd be like 1, 2, 3, 4, 1 here. But then the unit circle is here. Now, what if we took the vector, so instead of w, what if we took this vector, this little tiny vector there? I'm going to call it w hat. This is typical in physics and other subjects, is they put a hat over unit vectors. What that means is that I'm rescaling w, dividing it by its length, so that now it has length 1. So w hat has length 1. W hat is a unit vector. That means it lives on the circle. In higher dimensions, it would live on the sphere of the appropriate dimension. So a 3-dimensional vector that's a unit vector would be on the sphere. But yeah, so we say unit vector. What is a unit vector? It has length 1. How do we normalize a vector? So we normalize a vector by rescaling it so that it has length 1. So like the vector w has length square root of 17, but then w over the length is just, that's the same as 1 over the length of w. This is 1 over square root of 17 times w, which is 4, 1, which is just a long way of saying this is the vector 4 divided by square root of 17, comma 1 divided by the square root of 17. Now, this vector, which I'll call w hat, is a unit vector. Let's check. Let's take its length, the square root of the sum of squares of its components. Let's do this. Well, okay, so let's check what the length of w hat is. We hope that it's 1. Well, it's the square root of the sum of squares. 16 over square root of 17 squared is 17 plus 1 over 17. And yes, that is going to be 17 over 17, which is 1. Square root of 1 is 1. And we've succeeded in shrinking w, which was down to this little w hat. Okay. Now, let's go back to this, the relation of dot product to lengths and angles. Remember, the definition of the dot product is this. It's a sum like that. Where's it? Oh, here's the definition of dot product. We take the sum of the products of all these things. But the theorem about dot products is that it relates to the cosine of the angle between the vectors. Now, what if w was a unit vector? So if w were a unit vector, then this part is 1, or the length of w is, so v dot w equals the length of v times the length of w times the cosine of the angle between them. But that will just be the length of v times 1 times the cosine of the angle between them, which is just the length of b times the cosine of the angle between them. And now, if I have v here, and I have w like way over here, or really, no matter where w is, think about this. Here's the angle between them. And this is a side length of a right triangle that I drew. And its length, well, the hypotenuse is the length of v. This length, just this piece of it up to here, is equal to v times cosine of theta. But that is equal to v dot w hat. V dot w hat. So this is where unit vectors are really important for geometry, is that if we rescale the vector by its length, and by the way, because the dot product is what's called linear, which we'll learn more about, we can pull out this length of w factor. This is just a number. I mean, you can even remember, like, if w is w1, w2, w3, then w hat is equal to w1 over the length of w, w2 over the length of w, w3 over the length of w. Where, remember, the length of w is just a real number. That's a real number. And so we can pull it out, 1 over the length of w times w1, w2, w3. And so that's why we can take this number there and pull it outside. We can, now this is a real number times a real number, so we can change the order of them. I mean, all this stuff I was just talking about pulling this out and rearranging to the other side, it can be very confusing, but it's nothing that is like, I don't know. I mean, it's concepts that like 4 times 3 is equal to 3 times 4. Why? Because 4, it's just what multiplication means, is that, oh, that was 4 times 4. There's 4 times 3, and then maybe this is 3 times 4. I don't know. I'm just, like, this stuff can be confusing. And it's like, why can we pull this number from there to out here? Or from there to out here? And really, it's because of the definition of the dot product, which I didn't even write, so let me finish writing it. And then the idea that we can change the order of multiplication of real numbers. So this dot product here would be the sum of vi times wi, but now the components of this w hat are wi divided by w. And so this sum is really like v1, w1 divided by w, plus v2, w2 divided by w, plus blah, 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 blah. But in each case, we could pull out the length of w and have v1, w1, plus v2, w2, plus dot, dot, dot. Where in all the other terms, we pulled out this factor, which appears in the denominator of each of the components of w hat, and we pulled it outside, and that's why we can do this. And now we come to a very important concept, which will use this. And this is where you're going to see dot products being used in amazing ways in all of science, is to project things. And so this is probably the main concept that we're going to learn. And this is already half of it. So if this stuff was confusing, take your time with it, but wait until you see this so that you know why we're doing it. Okay. Now, what I'm going to do here is say that v and w, what I'm going to use is that I'm going to break v into 2 pieces. And the pieces look like, oh, that's a little, I want to have a good drawing. Hope that was okay. So, I mean, if I look through the line through W here, it looks like W is the vector 4, 1. And it looks like V is the vector 1, 3. Okay, so I've got the line through W, and I've got the line orthogonal to W, or the line 90 degrees with respect to W. And this line, this is a 90-degree angle, so 90 degrees, right angle line. It's the lines, we say orthogonal to W. We'd say normal to W. When something has a lot of names, perpendicular to W, when something has a lot of names, you can guarantee it's going to be important in math, because it has a lot of names because many people found it to be incredibly useful and gave it a name all over the world. And this is just in English. Imagine how many names it has in other languages from other mathematicians discovering these same useful properties. And so this is what we're going to do. We're going to break V into two pieces, the green piece and the pink piece. So project V along W. That will be a vector. That's the pink vector here. That vector. And my question is, how do we compute that? And now the green vector is project V maybe against W, or I like to say normal to W equals what? So it's that green vector. Now I'm saying, how do we compute this? Because if you're going to make video games and animations and scientific calculations and interpret data and do machine learning, you need to actually compute. So how do we compute the piece of V that goes along W? That's the green piece. This is the piece of V that is along W. And how do we compute the pink piece, the piece of V that goes against W, or normal to W, or orthogonal to W, or perpendicular? Okay, so we're going to compute the green piece first. So to compute the green piece, what we're going to do, and I'll say the formula first, is take V dot W. Okay, we're going to use the dot product to project V. What did I do here? I completely switched this. Oh my goodness. Okay. The green piece, project V along W, right? This part is along W. The green piece is along W, and the pink piece is normal to W. Okay, let's compute the green piece first. We're going to use the dot product, but then we're going to take the dot product of W with itself and multiply by the vector W. So this is a real number, this is a real number, this is a vector. Let's immediately compute it. So V dot W is 4 plus 3 times 4 times 1 plus 3 times 1 is 7. W dot W is 16 plus 1 is 17. W is 4, 1. Pause for a moment and just look at this formula so you can tell that this is a number, 7. This is a number, 17. And it's multiplying a vector, which is W. If we wanted, we can take it inside and get 28 17ths, comma, 7 17ths. But honestly, I'm fine with it leaving it that form too. This is maybe called the distributive law. This is how we multiply a vector by a scalar. Okay, so that's the answer. That is the answer. That's how we get this green vector. And let's even see, like, this number is maybe like 1.6. Like, twice of 17 is 34. So 28, 17 is like a little less than 2. And that's what it looks like, a little less than 1, 2. And then this number is a little less than a half, and that looks like the height. And so this is that vector. We've computed it. Now, why is that correct? Well, first, let's just see that the pink now is easy. The pink is easy. We just take V minus the green. So once we've computed the green, then we've immediately got the pink. Because if we take the vector V and we subtract this green vector, well, that puts us exactly at the tip of the pink vector. Subtracting the green vector from V gives us the pink vector. And so this part is easy once we've done this. And so this formula, this is what we need to understand. This is a super important formula. Now, why is it true? Okay, well, remember our picture up here. So I'll do it again down here. If we have some V, then it's the length of this line is the length of V, right? That's pretty clear. Now, if we have some W, and we want this piece. Now, how long is this vector? How long is this vector? Well, if this is the angle between, then this is the hypotenuse times cosine of theta. But that is V dot W hat. So not V dot W, but V dot W hat. And so then this is just a real number. It's just the length of this green vector. So if we want that actual vector, what we'll do is put it along W hat. But then we'll see that W hat, remember, is W over the length of W. W hat is W over the length of W. But this is V dot W over the length of W squared. I have 1, 2 of those. So I could just pull this one out of the dot product and put this one next to it and get a square. And then I have a W left over. But V dot W, the length of W squared is in fact W dot W. And that is where this formula comes from. It comes from the all-important, hypotenuse. Whenever we have a right triangle and we have an angle, and this is R, then this is R cos theta and this is R sine theta. And that should be automatic. No matter where you put the angle, if the angle is down here, then if this is R, this is R sine theta is opposite the angle. This is R cos theta, this is adjacent to the angle. And so that's really where it comes from. That combined with, this unit vector and the fact that, if the length of W is the square root of W dot W, well then W squared, the length of W squared, is in fact W dot W. So that's why we were able to do this and this. Take a moment, and really try to remember this all on your own. Quiz yourself. Can you recall all these steps? I wouldn't, the first time I was a student, I wouldn't have been able to remember everything here and re-derive it, rethink it myself. But try. And then when you get stuck, that's okay. Come back and rewatch this, rewind, and try again. This is super important. It's going to come up throughout. And if this can be fast, if this can be easy for you, this piece right here, then you're really set up for a lot of success on many problems that we'll see. Okay. So that's it. Now, let's just finish the problem. Let's find the pink vector. Well, the pink vector is just V minus the green vector, so V is 1, 3, right? V is 1, 3. So I subtract the green vector. Okay. This is sort of, it's not pleasant, but I can do it. So 1 is 17 over 17. 17 times 3 is 30 plus 3 times 7 is 21. That's 51. So 3 is really 51 17ths. minus 28 17ths, and 7 17ths. Okay, so I can do this now. 17 minus 28 minus 11. Hopefully that's correct. 51 minus 7. 44 17ths. Okay, so we have like negative 0.5 or 6, negative point something, and then a positive number, maybe a little less than 3. And that is indeed negative a little bit and positive a little less than 3. That is exactly what the pink vector is. So we have computed the pink vector. We have computed the green vector. We can now do a lot with a computer in many scientific problems. Yeah. Excellent.